All right, so you should now be able to see the screen where I'm going to be writing on. So this last function, this last discontinuous function that we're going to see is called the Dirac delta function. You don't have to remember that name. Your author also calls it an impulse function, which is more of a description. And how it's defined goes as follows. It's given by the symbol delta, lowercase Greek letter delta. Ooh, I did not mean for that to be blue. Just a second, let us get this into black. Just to make a difference between the name of the thing and the information that you need. So this is a really weird function, I'm not going to lie. It's a piecewise function, or discontinuous function, and it is almost always 0. Okay? It is 0 anytime t, your independent variable, is not 0. Like almost everywhere. If you graphed this thing, it would literally look like the x-axis, and then at t equals 0, so right there where the y-axis comes into play. I say x and y-axis, but really it would be t and delta axis. You then have an impulse, or a spike. So infinity, not really a number that you could put here for a normal real-valued function, which is why this guy is weird. This guy was originally formed from a limit where what happens, where you essentially have this going on. And I'm not going to make this super duper precise, but if this guy here was t, this guy here, which is normally your y function, I'm going to put as a name of our delta function. And you could build this in sequence as a limit by doing things like step function, then another step function, then another step function, then another step function. As these guys get narrower and narrower, they also get taller. So here's how this delta function was actually defined. It was defined as an integral. So specifically, people were like, hey, I need some function, we'll go ahead and call it delta, where if you integrate this thing from negative infinity to positive infinity, it's supposed to equal 1. Well, a lot of functions do that. But what they did was they said, hey, I need this thing to get skinnier and skinnier and skinnier. Notice here, this part where it says t not equals 0, t equals 0, that's actually putting the width of these little rectangles, making those widths smaller and smaller. Well, if you still need the area of those rectangles to equal 1, what happens? As the width shrinks, the height increases, and when the width shrinks to essentially 0, the height here is essentially in limit form going up to positive infinity. Okay. Now, does this actually occur in physical problems? The answer is actually yes. And this is why your author also calls them impulses, because this would be something where, I'm not going to lie, I think of this stuff in terms of electrical current, and this would be something where all of a sudden you have literally an impulse, literally a jolt or a spike in terms of your electricity. Okay. Can it come up in other places? Yes, those two. So if you need one of these guys to model your physical situation that you have, maybe your impulse, maybe your spike in whatever it is that you're measuring, the thing that pops to the very, very top of whatever instrument you're using, maxes it out to the top of however high your instrument goes. Maybe it doesn't happen at time t. Maybe it happens somewhere else. So it turns out that most people actually, when they're dealing with your delta function, shift it. So most of the formulas you'll see is something like delta of t minus a. This is the same piecewise function, so still 0, still the essentially infinity value, except now the impulse, that essentially infinity value, is at t equals a. So we just moved it. That was it. Turns out the Laplace transform of the delta function is given in terms of this translation. So your delta function, when you plug in t minus a, and this guy turns out to be e raised to the negative at. And I believe your book actually walks through how that formula got made. You run it through the definition of the Laplace transform, so you plug it in to an integral, and when you go through and evaluate it, well, it's 0 almost everywhere. You only have to evaluate it where you have non-zero values, and it turns out that's the part that doesn't cancel out at the end. I'm not going to go through all of that definition. I'm just going to give it to you. Now, once we have the formula for this delta function's Laplace transform, we can now start applying it to examples. So suppose you have this example down here, and you've got the function defined in two pieces. You've got t plus 6 times delta of t minus 2. And you, for whatever reason, need the Laplace transform of that. Well, just like what we've done in the past, we can do what? We can say, hey, well, this is the Laplace transform of t plus, well, you can always pull out coefficients, so 6 times the Laplace transform of our delta function. Now, we talked about the Laplace transform of t last time. Does anybody remember what the Laplace transform of t would turn into? So this guy would turn into 1 over s squared. Now, the 6 just hangs out because it's a coefficient. And if we apply the rule that we have for the Laplace transform to our delta function, the only thing we have to really figure out is what's our a value. So what do you guys think our a value is for our delta function? That way we can use our formula. Ooh, it's not going to be -2, but you're close. Yep, so it would be the +2. So what does that mean our Laplace transform of delta of t minus 2 has to be? Yep, don't overthink it. You just plug it into the formula right here. So it would be e raised to the -2s. And that's literally it. If you recall, the Laplace transform of our step function last time, or one that was also called the Heaviside step function, that one also had an e and then e multiplied by something in the Laplace transform of that step function. It turns out if you've got a discontinuous function that you're dealing with, when you take the Laplace transform, you always get some sort of e raised to something. That's actually the hallmark of identifying if you had a discontinuous function to start with. Okay? But that's it in terms of our delta function. There is no more. So that's it in terms of new Laplace transforms. Everything else for today is going to be inverse Laplace transforms. So let us look at the definition of an inverse Laplace transform, and then we'll start looking at different examples. So the definition of an inverse Laplace transform goes as follows, and it's right down here at the bottom of your screen. Suppose you're given some function, and I'm going to go ahead and call it capital F of s. If you can then find a second function, which we're going to call lowercase f, that's continuous on its domain where t here is 0 or positive, and you also get the equation that the Laplace transform of that lowercase f function equals exactly the original function that you had, then that tells you that that lowercase function that you found is in fact your inverse Laplace transform of the original function f. Now that's really, really wordy. What is that actually saying? It goes as follows. So it says, hey, you've got some capital F function. If that's the Laplace transform of f, then the function inside the curly braces, so the lowercase f of t, this is your inverse Laplace transform. In other words, you started off with the Laplace transform of somebody, you found the function here whose Laplace transform matched the original thing you had. In other words, we're undoing the Laplace transform operation. And the symbol to indicate that you're undoing that operation, notice, is the exact same symbol we use for the Laplace transform, that semi-cursive looking uppercase L for Laplace. The inverse Laplace transform has a little -1 up top. Don't put it as a 1 over L. That has no meaning here. This is just to represent inverse Laplace transform. So let's see if we can figure out some examples. Suppose you have this first example, and this first example says you've got the function 1 over s minus 7, and you want to know what function would have given us this Laplace transform of 1 over s minus 7. So this is literally what we're doing here to the side. So here's scratch work. What or whose Laplace transform gives us that 1 over s minus 7? Anybody have a guess of what type of function this might be? This would be one of our e functions. So if we go and we look at our Laplace transforms of e, we have e raised to the at is supposed to give us 1 over s minus a. So any guesses with that inverse? Yep, and several of you have already grabbed it. So in this case, what we'll grab here is that our a equals 7. So this guy is totally going to be e raised to the 7t. Bam, that's it. Huh? Questions? Make sense? Kind of feeling okay a little bit? It's okay to say a little bit. All right, so notice what happened. If you knew your Laplace transform rules, undoing them is typically relatively straightforward as long as it matches the format. So let's look at another example. Suppose you have this guy. In this case, I went ahead and had 2 pieces. But what do we know about Laplace transforms? If you have 2 terms and they're separated by a plus or a minus, multiplication is totally different. But if they're separated by a plus or a minus, you just take the Laplace transforms individually. We're going to do the same thing for the inverse Laplace transform. So this guy will turn out to be the same thing as the Laplace transform of the first piece, or the inverse Laplace transform of the first piece, and then minus the inverse Laplace transform of the second piece. And I went ahead and pulled out the 3, although you definitely do not have to. Anybody have a guess what type of function would give you the first piece and or the second piece? I've got a couple guesses coming in. First piece is definitely going to be a cosine. Anybody got the guess on that second piece? Yep, and that second piece is going to be dealing with a constant. So what you got to figure out is what our constants are. So this second piece right here, if we just look at it as 1 over s, is simply 1. Although if we looked at it here, and you have the rule of some constant over s being the Laplace transform rule that you worry about, this one would jump immediately to 3. Okay. So multiple ways that you could do this. Now, in terms of the cosine, we've identified that it's cosine. So the only thing that we have to worry about is, what is k? And in our case, what would our k value be? Right? It's always the square root of that number. So the number we had was 9. So the square root of 9 is 3, and it's always the positive square root. So if we put this all together, this tells us the first piece is cosine of 3t, and the second piece is negative 3 times 1, or just negative 3. And that's it. Notice in those last 2 ones, while I didn't write down the Laplace transform right next to it like we did in that first example, it definitely would have been helpful if we did, or you have to have those Laplace transforms at your fingertips. Now, for this semester, if you don't memorize the Laplace transforms, oh well, just make sure you have them in a list where you can easily reference them. Would you do better if you memorize the basic ones? Definitely. Why? Because it'll be more at your fingertips and you'll be able to go through the material easier. But that would be the basics in terms of how to do inverse Laplace transforms. Everything past that is just if your function that you're given is in a little bit more complicated format. So we're going to go over that. But before we go over the little bit more examples, I want to go ahead and show you what would happen with all of the inverse Laplace transform rules. So what I've done is I wrote out all of the Laplace transform rules, and then we'll figure out what we would do if we saw that format for the inverse Laplace transform. Okay. So what I did for us here is on the left-hand side, I wrote out all of the Laplace transform rules that we've talked about in the past. And then over here, I've put the standard format that you would see corresponding to the appropriate rule. Okay. So here's the ones that we just looked at. The Laplace transform of 1 was 1 over s. The Laplace transform of e to the t. The Laplace transform of cosine. Those were the 3 that we just looked at. So over here, if you look at the inverse Laplace transform of 1 over s, well, it would be 1. We just looked at that one. If you see the function 1 over s minus a, well, that just undoes the Laplace transform rule of e to the at. So you just figure out what your a is and write down e to the at. We dealt with cosine. So if you have that s over s squared plus k squared, you do have to figure out what k squared is, but once you do, you just have your cosine of kt. Those three are pretty much the easiest ones to see. Now, the third one down, you might expect to have a k on the top, but we don't. And the reason for that is not because you don't have to, and in fact, in previous semesters, I've totally put a k on the top there and just been like, bam, there you go. But it turns out that most people and almost all of my previous students have agreed that it's way easier to write this inverse Laplace transform if you have a 1 on the top. And the reason for that is with a 1 on the top, it clues into your brain of, hey, I may have to adjust for my coefficient. Okay? So let's see what this guy would be. Well, what do you really need? You really do need that k on the top. So if you really did need that k on the top, I'm going to put in some red writing right here, and we'll get rid of it in just a second. So suppose we actually put the k up top. Well, if we put the k up top there, we would have to have a 1 over k out front if we, at the end of the day, actually want a 1 over s squared plus k squared. So there's our adjustment factor. But now what do we have? We'll have the 1 over k from the coefficient out front, that red 1 over k. And now, inside the curly braces, we have exactly what we need for our sign. So this says we have 1 over k times sine of k times t. So that is a way of writing the inverse Laplace rule, transform rule, for sine. Okay? I'm going to go ahead and erase out the red scratch work here. Now, if you would prefer to have the k on the top, just cover up this 1 over k here and erase the 1 over k over there. But let me go ahead and erase off that red writing. I erased too much. Okay, apparently that one doesn't want to go away. So we'll just copy it up. So those are the basic ones for sine, cosine, e, and constants. Now, what happens when we come down to our next stripes? Well, the next two rules that we're looking at are sine and cosine, but when they're shifted. So sine and cosine when you multiply by e to the at. Notice in terms of the Laplace transforms, these two Laplace transforms are exactly the same as sine and cosine, except no, they're not. Every time you have an s, we've replaced it with s minus a. So the same thing is going to happen over here. I'll do cosine first because it's easier. If you have s minus a on the top, s minus a on the bottom squared plus k squared, it matches exactly what we have here. So this thing is totally just going to be e to the at. You'll have to spot where your a is, multiplied by cosine of kt. Now, the one we skipped looks almost identical to e to the at times sine of kt, and I'm going to be bold and then write that down, and then we're going to say, nope, that is totally incorrect because there's something missing. Anybody have a guess on what's going to be missing here? Yep. So this is that same exact adjustment that we did up here when we changed up for the inverse Laplace transform rule. We changed up the constant on the top from whatever k is to just a 1. We had to multiply by 1 over k. Same deal down here. And again, for most people, especially when you're first starting to do Laplace transforms, most people say that this is the easier rule to remember. But again, if you prefer the k on top, that's totally fine. And in fact, I often tell people as long as you know these rules over here, you can always go backwards really easily. Okay? As long as you're okay with dealing with constants. Okay. The last two rules that we've got that deal with sine and cosine were the two that we did at the end of class last time when we said t times sine or t times cosine. And we said that this was where we were going to take the first derivative of the Laplace transform of sine or cosine, take that derivative, and then multiply it by -1. Okay? And I told you that this is what they should equal. Well, what happens if you have something that looks almost identical to those Laplace transforms? Well, inverse Laplace transforms of those answers should be the original thing, and with cosine, it exactly would be. So here, if you have s squared minus some constant squared over s squared plus k squared whole quantity squared, that should be t times cosine of kt. Now, we're not going to see this guy too much just because we're not going to see too many quadratics squared in our denominator. But if you ever do see it in the future, this is where you're going to have some multiple times sine or cosine. Now, up here, this guy, the one that we skipped before, is s over s squared plus k squared whole quantity squared. Notice it's almost similar to our t times sine rule back when we were doing regular Laplace transforms, but it's not exactly the same. So what is the adjustment factor here? In other words, what am I going to have to multiply by our t times sine to actually make this rule correct? Anybody have a guess? Ooh, close. I've got a couple guesses coming in. Yes. So here, what did we have? Where'd it go? We don't have the 2k. So what we did right here is we just divided this constant of 2k on both sides, if you will. Well, if you divide this guy on both sides, we're going to end up with a, don't want to write with a highlighter, 1 over 2k. So just like with all of the other sign rules, you have some reciprocal, that's a reciprocal of a coefficient out front, or reciprocal of a constant out front. And that's it for our sines and our cosines. That's that same thing that we had right up there too. All right, so the next thing that we have is dealing with t to the n. So if we called it this, this would be like our power rule for Laplace transforms. And we found out last time that if n is some positive integer, you're going to get n factorial over s raised to the n plus 1. I swear that was trying to be a plus 1. Okay? So we found that out before. Well, what happens if you're trying to find the inverse of Laplace transform of something, and all you see is something like 1 over s to the 5th power? Okay? Well, in that case, you've got to match it up to this formula, and you have to match it up to like the 5th power would be n plus 1. You'd solve for n. Then you'd have to make sure your thing on the top actually works out correctly. So here's what we're going to do. I am going to claim that for this particular rule here, it's going to go back to a t to some exponent. Okay? So we'll write down the t. But to figure out what exponent, we've got to look at what's going on. So notice the exponent on the s is what? It's always 1 more than what the exponent on the t is. So here, if this guy, this n, this exponent on the s is 1 more than the exponent we want to have on the t, what should be the exponent that's on the t? Any guesses? Yeah, so we'll decrease by 1. So this guy would be n minus 1. Now, here's the second thing to look at. The second thing to notice is, in our original Laplace transform rule, we took the original exponent on t, and we have a factorial on the top of the fraction. Now, where should that live? That should live over here on top of the fraction. Now, do we have anything other than a 1 on the top of the fraction? No, which means there's got to be some sort of adjustment factor. So just like the 1 over k and the 1 over 2k that we had previously up with the sine function, or versions of the sine function, we're going to have a 1 over something, and it's going to be 1 over some factorial. Any guesses which factorial it's going to be? Yep, it is going to be the exact same factorial that matches your exponent on t. So notice here, the factorial matched the exponent on the t. Well, we just found that the exponent on our t was n minus 1. So that means we're going to divide by that same factorial. So divide by n minus 1 factorial. And we'll have a couple of examples dealing with these type of situations. Why? Because polynomials are relatively frequent. Okay. But let's finish off the rest of our, actually, I think I've got a little bit of space. So let's do a little baby example right here. So suppose we look at the following. Suppose we are asked, we said 5 before. Let's actually do that one. Suppose you want to find the inverse Laplace transform of s raised to the 5th power. I'm definitely regretting the 5th power right there. So what do you think that guy would turn into? What would be the inverse Laplace transform of 1 over s to the 5th? Don't overthink it. Yep, to all of you guys who typed in, all of you were right. So in terms of this, what do? We'll have t raised to the 1 less power, so that would be t to the 4th. And out front, we'd have 1 over 4 factorial, and 4 factorial is exactly the same as 1 over 24 times t to the 4th. And if you want to put t to the 4th on top and divide by 24, you totally can. Personally, I like writing things in polynomials more than in pure fractions, so I default here to writing this as a coefficient out front and then the t to whatever power next to it. And that's it. That's all you've got to worry about. Now, what happens if we have somebody that's not quite a polynomial? In other words, what if you have your exponent on your t to be something that's not an integer? So we talked about these, and this is where we had to break out our delta function. Now, I went ahead and wrote the two properties for the gamma function that we need when alpha is not an integer. Okay? So we have t raised to the alpha. On the bottom, it's s raised to the alpha plus 1. That's the same rule as when we had t to the n rule. On top, it's gamma raised, and you plug into gamma alpha plus 1. This formula works as long as alpha is some real number bigger than -1. And the things to remember here is gamma of alpha plus 1, and we did this in terms of x's last time, is the same as the alpha times gamma times alpha. And when you go down, eventually you're going to end up dealing with gamma of 1/2, and that is the square root of pi. Okay? Now, if we wanted to build the inverse Laplace transform of this formula, or that would correspond to this formula, notice it's going to look really, really similar to what we just did. Okay? First thing that we're going to do is we're going to figure out that this guy is going to be t to some exponent. Anybody have a guess of what exponent I should put on the t? Feel free to type alpha as a. It's way easier to do that. Yeah, so this would be alpha minus 1. So the exponent drops by 1. And then out front, because we don't have a gamma function up top, we just have a 1 up top, we're going to divide by a gamma function. Did not write that gamma function in a good way. Just a second. Let us try again. Start making it like a hangman symbol instead. That also is bad. There. Apparently I was just writing it from the wrong side for me. Okay. Now the question, of course, is what should we put inside of those parentheses? So anybody have a guess what we should put inside the parentheses? It'll be either alpha or alpha plus 1 or alpha minus 1. Not going to be alpha plus 1. Thing is, match it to or compare it to the exponent on t. In the original formula, the thing inside the gamma function was 1 bigger than the exponent on t. So our exponent on t right now is alpha minus 1, so add 1 to that, and it should just be alpha. Not going to lie, this is one of the harder ones to think about. But the thing is, this guy here, when you plug in, it'll be 1 bigger than that exponent. Or if you prefer, it'll match whatever exponent you had originally. Those are the two different ways of thinking about it. And we're not going to have too many of these examples, so I'm going to skip out on that one for now. When we do all of our other examples, we'll go and deal with it then. Then with these polynomials, we also looked at last time, or what happens if you have your t to the n multiplied by some e function. Well, the normal thing that happens when you multiply by some e function, you're just changing your s to s minus a. So notice these two guys are the same formulas as above. We just swapped out the s's with s minus a's. Now, what would that mean in terms of their formulas over here? Notice if we want these inverse Laplace transforms, they look identical to the original formulas we had right up top, except the s's are swapped with s minus a's. In other words, we had this translation, we had this shifting going on. In terms of your answer, notice here, what's the only difference? The only difference is we'd multiply by some e to an appropriate power. So for this first one here, what would this mean? You take the same exact answer that you would have had right up here. So we still have our 1 over n minus 1 factorial. We still have t to the n minus 1. And just because it's convenient right now, I'll write the e function at the end. This would be e raised to the at. So this shifting, this s minus a where an s should have been, that means you multiplied what you normally would have gotten simply by an e to the at, where a is whatever that shifting factor is. And that's it. So any guesses what we would do down here if we apply that exact same thought process? I realize now that I say that, that's probably difficult to type. So what we'll do is we will grab this same exact inverse Laplace transform rule we had before. Oh my, somebody did actually type it. Several of you. Awesome. Yes. Let me write what you guys said. So this would be 1 over gamma of alpha times t to the alpha minus 1. And then you just multiply that whole thing times, or raised to, you multiply the whole thing by e raised to the at. And that's it. And the only thing that's awkward about that formula is we have both an alpha and an a value. That's the only thing that's awkward about that formula. And this idea of multiplying by an extra factor of e raised to the at, if you switched out s's for s minus a, that's a really, really common thing. Actually, that's what we do pretty much all the time. All right, the last 3 rules right here deal with our discontinuous functions. So I'm going to put a little line here. Below that line are all of our discontinuous functions. Our unit step function from last time was e raised to the negative as over s. We had, if we multiplied our unit step function by some other function, it would be e to the negative as times the Laplace transform of that other function. And the new one we had today, the delta function, was just e to the negative as. Notice for all 3 of these, you have this factor of e to the negative as. That's the key, or that's the indicator that says, hey, you've got a discontinuous function involved. Which means if we start looking over here at our inverse Laplace transforms, notice there's no shifting, there's no multiplying or dividing by a special constant. It's literally, if you see e raised to the negative as over s, that's just going to turn into your step function. If you see e raised to the negative as multiplied by some other Laplace transform, well, you figure out what the inverse Laplace transform of that guy is and replace the t with a t minus a multiplied by your step function. So this one might actually be easier to read as step function multiplied by the Laplace, or really inverse Laplace transform of the f function, where you replace your t with a t minus a. Is what you actually do there in terms of what those symbols meant. And the last one is if you just have the e raised to the negative ast, that turned into the delta function. So those guys were straightforward, just reverse where you're looking in terms of the Laplace transform. And the only thing that we haven't talked about down here at the bottom is properties There's one property and then some strategies. And we'll get into the strategies in a little bit after we do the first couple of examples. The properties, this one here are reviews. If you're applying taking the transform, you've got a couple different terms. On pluses or minuses, you can break up and look at the individual inverse Laplace transforms. And the coefficients, if they're constant, you can pull the constant out front as coefficient in front of the inverse Laplace transform. The same thing you can do with limits and derivatives and integrals and regular Laplace transforms, you can still do with the inverse Laplace transforms. And here's, while we're talking about it, here are the big techniques that we use. When we're dealing with our inverse Laplace transforms, we are dealing with fractions. So one of the big things that we look for is you look for, does it look like a formula? I know, except there, instead of an s, there's an s minus a. Hey, that means there's going to be an extra factor of e raised to the at. We talked about that already. Second thing is, and this deals with sines and cosines, specifically if you've multiplied an e factor by a sine or a cosine and then took the Laplace transform, on the denominator you have s minus a squared plus k squared. Well, normally it's not kept in that way. Normally people actually multiply it out, distribute it out, and make it one polynomial in the bottom of your fraction. Scroll up to, sure, where are you looking? Is this good? Okay. So if you're looking at fractions, one of the techniques we use is completing the square, and that deals with if you have either sine or cosine multiplied by an e to the at function. We'll have several examples of how to tell when to use completing the square. And the other thing that we do when we look at the fractions is partial fractions. Note that completing the square and the partial fractions, those are the same two techniques that we use when we're dealing with integrals when we have a complicated fraction and we're trying to get it into a usable format. So those same algebra techniques that we've had in previous classes, or specifically Calc 2, they come back. Why? They're algebra techniques that people use to simplify fractions or make fractions easier to deal with. But that's everything in terms of the rules and structure that you need for the inverse Laplace transforms. And I'll go ahead and put this into a PDF form and post it on Canvas for you guys, or create your own little document like this, either way, so that you have a reference somewhere of all your Laplace transforms. And if you like to have the inverse Laplace transform rules written out, here's what the ones, here they are, at least of the ones that we're going to use. Are there more Laplace transform and inverse Laplace transform rules out there? Yes, but we're not going to deal with them in our course. Oh. All right, so let us get to examples. Did everybody see what you needed to on this sheet for right now? Got all the rules that you wanted to write down? If the answer is no, do a shout out. Otherwise, I'm going to go back and we're going to look at some more examples. Oh, yes, since we scrolled back up. And we'll talk about these more in depth. I'll actually write them out on the examples we'll use them for. So the three things to look for is, does it look like you've switched out an s for an s minus a? That one, if you've written out the inverse Laplace transform rules, will probably already be taken care of. So the big ones to really remember here are completing the square on the denominator, if applicable, or factor the denominator. So you always check, does it factor? If yes, use partial fractions. If your denominator does not factor, then you complete the square. Okay? So these are the two big techniques. With completing the square, you're always going to turn into some sine or cosine or both when you take the inverse Laplace transform. With partial fractions, linear factors turn into an e. Quadratic factors turn into sines or cosines. And repeated factors typically turn into an e function times a t to the n function. And if you really get complicated, which we're going to try to avoid, you can actually get those terms that would convert into t times sine or t times cosine. All right, but we'll come back to this when we need it for our examples. So if we jump back to our examples, the first one I've got is a relatively straightforward guy. So suppose you've got this guy right here, and you wanted to go ahead and figure out the inverse Laplace transform of 1 over s squared plus 9. First thing you want to identify is what type of function do you think it's going to turn into? Anybody a guess of what type of function this guy would turn into? Yep, so this guy is totally going to turn into sine, so I'm going to write little scratch work down here. And if it turns into sine, the thing that you've got to figure out is you've got to figure out what the k value is. Any guesses what the k value is here? So this one would be 3, which is a positive root of 9. So this means we're just going to apply this rule. So I'm going to say that this looks like sine of kt, so sine of 3t. And is that correct, what I've just written? The answer is no. What happened, we had our original 1 on the top of the fraction with sine. We always multiply whatever the constant is on top by the reciprocal of k. So in our case, you guys are totally right. We need a 1/3 out front. But that's it. That's how you would deal with this guy. Now, what happens if you have this next guy? So this next guy says, let's take the inverse Laplace transform. And it's 1 over s to the 4th minus 3 times s to the 3rd plus 1 over s squared. And of course, you could, if you wanted to, write this as the inverse Laplace transform of 1 over s to the 4th minus 3 times the inverse Laplace transform of 1 over s cubed plus the inverse Laplace transform of 1 over s squared. You don't have to do that either. Now, if we want to go ahead and start taking the inverse Laplace transforms of these guys, what rule are we going to be using? Anybody have a guess? In other words, what type of function are these guys going to turn into? They could turn into all different things, but in this case, actually it's the same rule for all 3 of them. It's the t to the n rule. So we're going to have all of these guys turn into t to the n, and I should move that to a more convenient location. Okay. And I'll put quotes around it because our n's will be different. Now this is the point in time where you can decide which of these types of rules you want to use. So if we go back to our list of all the different Laplace transform rules, we see that we could actually use, I'm going to try to get this so you can see it at the very top. There we go. We could just use the regular old Laplace transform rule, or we could go ahead and use the inverse Laplace transform rule where we already have a 1 over s to the n. Okay? Most people find this one much easier to use even if they don't use any of the other inverse Laplace transform rules. So I'll go ahead and use this one. So notice what we're going to need to figure out. We're going to need to figure out what this n is. In other words, what's the exponent on the s. Now, there's 3 different parts of the example that we have. The first part is 1 over s to the 4th. So the n value for this first one is going to be what? The n value here would be 4, but in terms of the exponent that t is going to be raised to, t would be raised to the 3rd power. Okay? So we'll subtract 1 from the 4 to get the 3, and then we'll have as a coefficient, we'll have 1 over, anybody remember what that coefficient was that we just looked at but now is not in front of us? Right, it would be 1 over 3 factorial. The 3 factorial matches the exponent here, and 3 factorial is, of course, 6, which is what you guys are telling me. So that would be 1/6 t cubed. Now, if we look at the second term, we have 1 over 3 cubed. So here our n is now 3, but what would the exponent on the t be? It would be t raised to what power? Huh? And what would be the thing that we multiply out front? It'd be 1 over something. It'd be 1 over 2. And in our case, technically the formula says it's 2 factorial, but 2 factorial is exactly the same as 2. Now, last term is 1 over s squared. So here's where our n equals 2. So you guys tell me, what do you think that last term is going to turn into in terms of t's? Yep, this guy turns out to be just plain old t. The exponent is 1, and then you have 1 over 1 factorial, which is still 1. So if we go ahead and write this guy out, we would have 1/6 t cubed minus 3 over 2 t squared plus t, and notice we just built ourselves a polynomial. So if you're going to end up with a polynomial, the stuff inside of that inverse Laplace transform, the stuff in terms of s's, is all going to be some constant over s to the n in terms of formatting. Okay? And that's it for that one. These type of guys come up a lot, so I would definitely recommend memorizing this rule with the 1 over s to the n, just because it does come up a lot. Okay. So next example that we've got is trying to find the inverse Laplace transform of a fraction. On the top of the fraction is s minus 1. Bottom of the fraction is s squared plus 4. Any guesses what type of function this guy is going to turn into? Answer is yes and no. So it will turn into a cosine. It will also turn into something else. Anybody have a guess what else it's going to turn into? Nope, it's not going to be a shifting one. And it's not going to be a shifted one because down here we simply have an s squared and then a constant. So the denominator here is in the form of s squared plus k squared. So that means it'll just be a cosine of kt or a, ooh, I've got somebody. So this one here will be both a sine and a cosine. Now, how could I tell? I'm going to split this guy up. I'm going to split it up on the numerator, so on the top. So this is going to be s over s squared plus 4. Pretend that symbol was a 4. Minus the inverse Laplace transform of 1 over s squared plus 4. Now, do a quick double check here. Do you believe that algebra? Algebraically, is that an okay way to split it up? And the answer is, while you're not allowed to split it from the denominator, pluses and minuses in the numerator is totally a perfectly fine place to break your fraction into 2 pieces. Now, once we've split this up into 2 pieces, it's probably a lot easier to see what's going on. This first piece right here with just a single s, that one will turn into your cosine. And this piece right here with a 1 on top, that one will turn into your sine. So I'm going to go ahead and write that. So here's cosine something minus sine of something. Now they have the same denominator, which means they're going to have the exact same k value. So what would be the k value in this particular case? The k would be 2, so yep, you get cosine of 2t, sine of 2t, and you're totally right. There has to be something in front of that sine, and that's where that reciprocal of k is, that 1/2. Yep, so that would be how you would deal with these guys. It is extraordinarily, and I cannot stress enough how common it is to get something that looks like this, where the denominator is the correct form for either sine or cosine, and the top is where you've got the appropriate part for cosine and you have the appropriate part for sine added together. Remember back to when we were dealing with differential equations and back when we were doing things like method of undetermined coefficients, what happened when we got imaginary roots from our not method of undetermined coefficients, just homogeneous equations. We would get our characteristic equation, we'd solve for the roots, we'd get imaginary roots. What happens with our solution? We get a cosine and we got a sine. When we start putting this or dealing with differential equations, this is like dealing with those imaginary roots. You get a cosine and you get a sine part. Okay? So those guys will often come together in pairs, and it's where the 2 different fractions were just added together, and you have to essentially unadd them or separate them. And that's it for that example. Now the next example, I set it up to be almost identically the same. Okay? There are some differences. Can anybody spot the difference between that last example labeled with an E and this next example labeled with an F, besides the +4 on the top? So the key thing to notice here is we've got what? Previously, we had an s squared plus some constant. Down here, we now have an s minus 1 quantity squared plus some constant. So what this guy here is telling us, you can actually ignore the top. It's the bottom that's going to give everything away. What this tells us is you're going to be looking at e to the at times cosine kt and or e to the at times sine of kt. Now you can actually tell that you're going to have both of them here. Anybody have a guess of how or where we could spot that we're actually going to be dealing with both of those two functions when we get to the final answer? It's subtle. The bottom of the fractions tell you what function you're dealing with. The s minus 1 instead the s tells you you're going to multiply your sine and your cosine by the e to the at. The fact that you're going to have both sine and cosine actually comes from the, seeing no answers come in, comes from the top or the numerator. Now, why would I say that top or that numerator is going to tell you that we're going to have both a sine and a cosine part? Because for cosine, you need the s's, and the sine, you need just the constants. So the fact that we have an s plus 4, that s plus something, tells you a cosine is definitely going to be involved. And the fact that the top is not s minus 1 tells you there has to be a sine involved as well. Okay? Because remember, over here to the side, what did we have? Our rule was s minus a on the top, bottom, s minus a squared plus k squared. That's the guy that gave us e to the at times cosine of kt. So let's break this up. We're going to break this guy up into two fractions, almost exactly like we did last time, except we're going to be a little bit more strategic about it this time. So we want to be able to use our inverse Laplace transform rule for cosine times e to the at. So on the bottom, we have the right format already. We have s minus 1 squared plus a 4. Then we're going to have our second fraction over here, which is still going to be s minus 1 squared plus 4. Now, this tells us that our a is what? A couple of you already said what it was. In this case, our a is 1. Anybody grab what our k is? Not that we actually need it right now, but just to have it here for us, our k would actually be 2, that positive root of 4. Now, according to our formula over here to deal with e to the at times cosine, what do we need? We need s minus a on the top. Well, s minus a is always whatever's inside of those parentheses that's being squared in the denominator. So I'm going to force it. I'm going to actually write s minus 1 on the top right there. So that's our s minus a. Now, over here, what are we going to do? Well, we're going to go ahead and make sure that the sum of these two things really does equal what we were originally given. So anybody have a guess of what we would need to add to s minus 1 to get s plus 4? Ooh, it's not going to be plus 3. It will be plus 5, though. Don't put the s. Total mistake. We'll get rid of that quickly. Now, once you write your guess down, go and add it together. Make sure it's actually right. So quick check. If we have s minus 1 plus 5. So minus 1 plus 5, is that plus 4? Everybody nod your head to yourself. Yep, that works. So this is our way that we break up or we split or we separate our two pieces into two smaller fractions. Now, in order to do this, we already found out what a was, and we actually already found out what k was too. So we can go ahead and actually get our answer. So for that first guy, this matches exactly with our rule for cosine times an e. So we'll have e raised to the t times cosine of 2t. Now, anybody have a guess what this second term is going to turn into when we convert it into t's? So for this one here, the adjustment factor would be the coefficient. Oh, you can't hear me very well. The adjustment factor would be the 5 over 2, the over 2 because that's the 1 over k. So here we have 5 times 1 over k. Then we'd have the e to the at, so that's e to the t. And this guy is our sine version, so sine of 2t. Yes, the key thing here is you can go ahead and pull that 5 out front, and especially if you're using the rule that we did before. What I didn't do up here, and we probably should have gone ahead and done, is pull that 5 right out front and kept that guy on 1. Yeah. Okay. Questions make sense? Kind of okay so far. So all of the examples that we've had so far are relatively, not perfectly, but relatively straightforward applications of all the rules. Okay? No special techniques other than these two guys where you broke the fraction up into 2 pieces strategically so that you have a sine component and a cosine component. Okay? The next couple of examples that we'll end today on are going to be ones where you actually have to do a specialized technique. Okay? So let me write down those techniques that we dealt with previously, or that we had listed out previously is on the other page. So these are the specialized techniques. We have looking for translations, that's identifying if you're going to have an e to the at in your answer. But if you've gone through all those inverse Laplace transform rules, those should come up relatively naturally through the rules. Okay? So the big ones are looking for completing the square. And that's specifically completing the square in the denominator. This is when you would do this when your denominator doesn't factor. If it does factor, don't do this. Now, what's going to happen if you complete the square? If you complete the square, you're always going to end up with the denominator of your fraction looking something like the last example we just had. So it will always be a sine or a cosine with an e involved. So this gives you back e to the at sine of something, e to the at cosine of something, or both of them. And the last thing that you deal with is we're going to deal with partial fractions. How do you know you're going to be dealing with partial fractions? You get somebody that doesn't look like one of our rules, and the denominator does factor. And in this case, depending on what the factors are, is what you're going to get back. So if you have a linear factor, this guy is going to turn into an e to the at form. If you have a quadratic factor, this guy is going to turn into a sine or a cosine without the e's in front. And if you have some sort of repeated factor, most of the time this is going to turn into e to the at times t raised to some power, but it could also have been, if it's a repeated quadratic factor, t times sine or cosine. All right, so those are the techniques, and now we can scroll up and down. Maybe that'll be easier for us in the future. So let us look at the first example I've got prepped up for us. And the first example I've got prepped up for us is this guy. On the bottom is s squared plus 2s plus 5. And on the top, we have 2s plus 1. So the first thing that you look at, you say, does this guy look like any of our denominators of our straightforward rules? What do you guys think? Does this look like any of the common denominators that we've been dealing with over the past couple days? And the correct answer here would be a big fat no. There's too many terms. So if it was just an s or just an s squared on the denominator, it'd turn into some t to an exponent. If you had an s plus 5, it'd turn into an e to something. If you just had the s squared and plus 5, that would turn into a sine or a cosine. But the fact that you have all three of those terms, that means it's not like any of the normal formats. So the next thing you look at are two things. You check to see if it factors. If it factors, we're going to use partial fractions to separate this into two smaller fractions. If it doesn't factor, we're going to complete the square. So looking at that guy, what do you guys think? Does it factor or not factor? Oh, I like how some of you are voting. So yeah, this guy is not going to factor. So that means for this particular example, we are going to need to complete the square. And that does mean that once we complete the square, it is going to look extraordinarily similar to our very last example that we had. Okay? So once we complete the square on this guy, it's going to look really, really similar to this last guy where we'll have something squared plus some constant. And up top, there'll be the same stuff we currently have because we won't touch the top. So let's go ahead and complete the square. So just like when you completed the square in Calc 2, we're only going to complete the square in the denominator. So we've got s squared plus 2s plus 5. You don't have any equals involved. So we look at the parts with s, so the s squared and the 2s. I'm going to put parentheses around them, put the plus 5 at the end. And anybody remember what we add inside of those parentheses? It is. So it's going to be a 1, and this guy is totally going to be b, whatever the coefficient is on the s. It's b divided by 2 whole quantity squared. And you always add it to that inside factor. Why? Because when you square something, the constant term is always positive. The term with the s right here could be positive or negative. That's fine, but this constant term will always be positive. Now, if you added something here, it changes what this expression is. So whatever you add, you also have to subtract. And at this point, we're just going to simplify. So we'll go ahead and we'll simplify this guy. The part inside the parentheses is going to be something squared. The part outside this parentheses is going to be plus 4. Anybody grab what was inside those parentheses? Hint, it's going to be s plus or minus something. I'll give you the other hint. It's going to be plus or minus 1. So what do you guys think? Positive? Should we do a plus, s plus 1 or s minus 1? That makes it easier to answer. So this one would be plus 1. So what this tells you then is we have the Laplace transform, or really the inverse Laplace transform of 2s plus 1, which we'll deal with in a second. And on the bottom, we have s plus 1, quantity squared plus 4, and that was actually way closer to the last example than I meant it to be. Oh, well. So at this point, we then need to break stuff up. Okay? Good so far, kind of okay so far. The main thing is remembering how to do completing the square. Once you've completed the square, we then get it in the format that we dealt with previously. Now, there is one extra hitch with this problem that was different than our last example, now that we're in this standard form that we can use a rule on. Anybody notice the thing that's different from our last example? It's kind of sneaky, but you got to deal with it. Yeah, it's that 2s. So we're going to have to deal with that guy. So here's how we're going to deal with it. Whoa, did not mean to highlight that. What that means is we're going to have a coefficient on the cosine part, is all that means. We're going to be able to pull that 2 out front. So when we break this thing up into a cosine and a sine part, so this guy is going to be cosine, sine. It is going to be multiplied by an a, wow, that's not the right thing, e to the at. So we need to figure out what our a is. Anybody have a guess what our a is? And while you're guessing, I'll copy down these denominators. So the a here is going to be -1. You always flip the sign right here. So if it was a -1, it'd be +1. If it's +1, it'd be -1. Now, what does that mean? This means that you need an s minus, not an s minus 1, an s minus a on the top. In other words, you need an s plus 1 on the top. Except we also want to factor out the 2. So if we want to factor out the 2, the top actually needs to be 2 times s plus 1. But 2 times s plus 1 is really 2s plus 2. So that's my scratch work. I'd say over to the side, but it's really beneath. So I'm going to go ahead and put the +2 right here. So you always focus on the one that's going to turn into sign, the one that has the s's involved, and then whatever's left over, that's the part that spills into the sign, the one that only has the constant up top. So if we have to have 2s plus 2 on this first numerator, but the sum has to equal 2s plus 1, any guesses what's going to be on the top of this second fraction? So this would be -1, and if it helps, this is the scratch work we're doing. 2s plus 1 equals 2s plus 2 plus unknown. Solve for the unknown. So let's put this all together. What do we have? We can rewrite this thing past the scratch work. So this is now the inverse Laplace transform. I'm going to pull the 2 out front. So this is s plus 1 inside the top of that first fraction, s plus 1 squared plus 4 in the denominator. And then the second one, pulled the negative out front. So we have the inverse Laplace transform of 1 over s plus 1 quantity squared plus 4. Notice the most complicated part of dealing with these inverse Laplace transforms is just if they need some sort of algebra adjustment, doing that algebra adjustment to get it into a form that you can deal with. So at this point, we've done these guys before. So the first one turns into a cosine. It's going to be 2. I lied, there's an e involved. Just a second. And e's are supposed to go in front. E raised to the at, so that's -t. And then cosine of 2t, where k here was 2. Then we have a subtraction. We have an e to the -t, sine of 2t. Anybody remember what the coefficient out front here should be? Is it good like it is, or do we need a coefficient there? And the answer is we totally should have a coefficient, and you guys are sending it in right now. It should be 1 over k or 1 over 2. And that would be our final answer. Notice they've got the same e to the at, one sine, one cosine, same angle inside of 2t, and then we just had different coefficients out front. All right, let us get away from sines and cosines. So next, and what looks like last example for today. So suppose you're looking for the inverse Laplace transform of this guy. The bottom of the fraction is s squared minus s minus 2, and the top of the fraction is also 2. Notice, just like our last example, this guy is not in a standard form for any of our rules for either Laplace transforms, or if you're looking at the inverse Laplace transforms rule, this one's not standard form. Why? Because it's got all 3 of those terms in the bottom. So this is where you check, hey, can I factor that denominator, or do I have to complete the square? So what do you guys think? Can we factor this one, or do we have to do complete the square? Ooh, I've got some answers coming in. Yep, this one is definitely one where we can factor it. So this guy here is going to be, well, if we factor it, we've got, what is that, s minus 2, s plus 1. Do a quick double check that I got the right factors there. And since we're a little tight on, wow, I'm reading the wrong word. Since we're a little tight on time, I'm going to jump us through partial fractions quickly. So we've done partial fractions before. Same idea here. you would have 2 over s squared minus s minus 2. And your two fractions will have their denominators of s minus 2, s plus 1. They're both linear factors, so they'll have a capital A, a capital B on top, and you just have to solve for that capital A, capital B. So the standard is to do cross multiplying, so we'll have 2 times A, s plus 1, and then we'd have B times s minus 2. We plug in a 2, we plug in a negative 1, and I'm just going to tell you here that, hey, we'll actually get that A should equal 2/3, and B should equal negative 2/3. Now, what does that mean for us? That means we can rewrite what we're given as follows. This is the inverse Laplace transform of 2/3 A times 1 over s minus 2. You could put the 2/3 on top, that's totally fine. And the second fraction turns into negative 2/3 times 1 over s plus 1. Notice I just did algebra to clean up the stuff inside the curly braces. Now, once we're here, notice what happens. These two fractions both came from linear terms. Both of those guys have an inverse Laplace transform of what type of function? Anybody remember? Yeah, it's going to be e to the at. So here, in the first one, our a would be that 2. What would the a be in the second one? It'd be negative 1. So for the first term, this turns into coefficient, the 2/3, times e raised to the 2t, 2's a. For the second term, you get the 2/3. And here it's e raised to the negative 1 times t, or negative t. And that would be it for that guy. So notice partial fractions, especially when you get these linear terms, you're going to get into a bunch of e's. If you recall back to when we were doing solving homogeneous differential equations, what happened, we often would get back solutions that had components that were a bunch of different e's, like this guy, or we had ones that came from imaginary roots of the sine and the cosine. So we're going to get that same sort of thing coming back. So things like partial fractions and completing the square, I'll be honest, they're really common to see when we start jumping into applying this stuff to differential equations. We're at the point right now where starting next week, we have enough information to go ahead and actually have all of the rest of our examples be starting with a differential equation and running through the process of pushing it through a Laplace transform, getting the answer, then finding the inverse Laplace transform to get the final solution of the differential equation, or technically initial value problem.